Buildings. There are a lot of them. You're probably in one right now. And that's why they're important. Because you're important. Welcome to This Week on Fun with Buildings. Today, we're taking a look at the structure of the London Stock Exchange Tower. Located on Old Broad Street in the heart of London's financial district, this building is 100 meters tall, which makes the math easy. The Stock Exchange Tower was used as a base model for our dimensioning decisions and also for the parameters of our simulation, such as the average London wind speeds. Today's objective is to find the best way to create the support frame structure of a building to withstand wind loads. Specifically, our objective is to find the combination of beam shape and beam material that would minimize the sway of the building. For the purposes of this study, we're analyzing three types of beams: I-beams, T-beams, and rectangular tubes, and three materials: concrete, structural steel, and aluminum alloy, all of which are commonly used in buildings. These materials have different properties: density, modulus of elasticity, and yield strengths for both tensile and compressive forces are just a few. Thus, they perform the best in their own unique situations. For example, while concrete is very resistant towards compressional stress, it does not perform well to tensional loading, whereas aluminum performs almost equally well in both tension and compression. The beam shapes also have their own properties, such as their unique abilities to resist multiple types of loading, such as torsional loading. The question is, what if we combined the weakest material in tension with the strongest shape in tension and compared it against the combination of the weakest material in compression with the strongest shape in compression? Now, which would fare better when bent from wind loading, which applies both compression and tension? Now, it becomes a bit more convoluted, and we're here to clear things up. Our hypothesis is that the strongest beam will be the steel rectangular tube. This is from the simple assumption that the strongest combination will be of the most versatile shape under different loadings and the material with the highest yield strength. The motivation for this research is to uncover any missed potential that could be exploited from different combinations. Otherwise, this research would confirm that the combined strength of the beam is directly proportional to the independent merits of the material and the shape of the beam, in which case our hypothesis will be correct. Ultimately, this will show out of the most commonly used material beams and shapes, which would be the best if we are to keep buildings, especially the taller ones, steady and safe.
In order to simulate our problem, we used ANSYS. Specifically, we used the static structural workbench. Since we are varying two parameters, the shape of the beam and the material of the beam, each of which has three options, a total of 9 simulations were conducted. After initializing our choice of materials, our simplified model of the London Stock Exchange Tower was created. Pulling a model off the building from Google Earth, we measured the area of the base and simplified it down to a square. We then assumed a 3x3 grid for the wireframe for each of the 26 floors, stacking up to a height of 100 meters. The three types of beams mentioned in our introduction were dimensioned to match the standard for buildings 10 to 40 stories tall. We then ran one type of beam throughout the whole wireframe. The walls were then added and designed with a standard thickness of 7.25 inches. After assigning the materials of each body, the walls being concrete and the beams being one of the three presented options, a gradient pressure was applied to one face of the building to simulate the wind loading. A gradient pressure was chosen due to the fact that wind speeds are faster at higher levels in the atmosphere. A time frame of 60 seconds was used. To gather our data, the maximum directional deformation along the axis of the wind load was probed. A simulation was also conducted using the modal workbench to find the natural frequency of the buildings. This information will later be used in the calculations to validate our results. From the simulations conducted, we were able to obtain results concerning the displacement of the building with respect to the independent variables of shape of beam and material properties of beam. We were attempting to identify a correlation between the material properties and the type of structural beam being used. However, the evidence left this target to be inconclusive. It was found that regardless of the beam structure, the material properties of the structural steel would always yield the lowest deformation of around 0.2 millimeters. On the other hand, regardless of the material properties, the rectangular tube beam would always yield a deformation result of around 0.2 millimeters once again. Many graphs were created to try to map certain combinations together. However, it was found that including a combination of both structural steel and the rectangular tube beam would not significantly decrease the deformation incurred as opposed to one or the other. On the opposite side of the spectrum, the concrete and T-beams consistently yielded results of high deformation rates at the top of the building, thus demonstrating many issues with tensile strengths of these materials. Now, discussing the validation of the results, two methods of validation were used. There was the validation of the material properties, and then there was a validation of the beam structures. We already discussed the characteristics of these independent variables, but not necessarily as part of the building. To validate the results for the material properties, the frequency simulation developed for the modal analysis is used. From the natural frequency property obtained, we discovered an analytical solution for which we would be able to obtain the sway and displacement of any building under critical damping. The second order ODE to model displacement of a building with damping could be modeled as the equation shown.
The sway of the building is modeled using Newton's second law and Hooke's law. Combining both equations and accounting for external load due to wind, we find the ordinary differential equation modeling the motion of the building, where the second derivative of u is the acceleration of the building, the first derivative of u is the velocity, and u is the displacement of the building. The other parameters include k, being the stiffness of the building, c, the damping constant of the building, and m being the dynamic mass of the building, along with p being the forcing term, or the force as exerted by the wind. To find the dynamic mass, we first find the total mass of the building. To do so, we first find the mass of the frame, which is equal to the density of the beam material multiplied by the area of the beam base and multiplied by the total length of all the beams in the structure. Using the length of the base and the height of each floor, we derive the equation to find the total length of the beams that are included in the building. We then find the mass of the wall by multiplying the density of the wall material by the thickness of the wall multiplied by the area of the wall, multiplied by 4 walls. We simplify the area of the wall into the multiplication between the length of the base and the height of the building. After finding the mass of the frame and the mass of the wall, we sum them to find the total mass of the building.
Afterwards, we can find the mass moment of inertia at the center horizontal axis of the building by using the following formula. Using the parallel axis theorem, we can then find the mass moment of inertia at the base, since that will be the pivot of the wind bending. Next, we can find the dynamic mass of the building by dividing the mass moment of inertia at the base of the building by the radius of gyration squared. In this case, the radius of gyration is the height of the building at 100 meters. In order to calculate the stiffness constant of the building, we can approximate the behavior of the building as a simple spring. Now, using the following equation that relates natural frequency, which was found through the modal analysis through ANSYS, and the dynamic mass, which was found in the previous calculation, we can find the stiffness constant. Next comes the damping constant of the building, C, which can be calculated as 2 times the damping ratio of the building multiplied by the natural frequency and the dynamic mass of the building. The damping ratio of the building can be found as the mass-weighted average of that of the materials in the building. For example, the damping ratio of the building can be calculated as the damping ratio of the material of the wall multiplied by the ratio of the wall to the entire building, summed up with the damping ratio of the frame material multiplied by the ratio of the mass of the frame to that of the entire building. Next to be calculated is the wind load. In order to do this, a reference wind speed at a reference height must be known. The wind speed can then be calculated at every height using the following formula. The alpha value is the wind shear constant based on the geographical area. Solving for the velocity variable and subbing it into the equation for pressure yields the following. The coefficient of 0.613 is based on the American Society of Civil Engineers Code. It is a result of the calculation based on typical values for air density and gravitational acceleration. The amount of area in contact with the wind is simply the length of the base multiplied by the height of the building. Finally, the force of the wind can be calculated by area multiplied by pressure. A final substitution into the ODE derived in the beginning can be solved to find the maximum displacement of the building. Since in our situation, displacement is directly proportional to deformation, these calculated values can serve as a means of validation.
Values in the ODE, we substituted the values for structural steel, concrete, and aluminum alloy into the equations. From this, we were able to solve for the constants within the second order ODE, which is widely used to model building sway, such as that of Type A 101. Basically, from a paper based on Type A 101, we were able to find this equation model. Next, this equation was input into Maple to solve the differential equation. With the enormous differential equation, we were able to plot the building's displacement with respect to a time interval of 0 to 60 seconds. What we could see from the plots of the three different materials when using the I-beam as a consistent structural beam variable is that the maximum displacement of the building at the top story was nearly 2 orders of magnitude greater than the deformation obtained from the ANSYS simulation. We will discuss the reasons why when paired with the structural beam results. Thus, the structural steel held the least deformation, while the concrete structural beams incurred the largest beam deformation, or displacement, through the analytical solutions. More improvements that could be made to accurately match the analytical and numerical results would be perhaps extending the complexity of our building, as well as adding more complex factors to the building ODEs. Moving on to the second point of validation, we need to discuss the beams. For this part, we pulled up a paper to vary the way we validate our sources. Through a study made by Mr. Ali and Mr. Moon, we were able to determine which type of beams serve to work the best within tall structures, and how the trends in current building designs are swaying. Though not many numerical models were developed in this paper, the author described the effect of certain loads on different types of buildings. One of the building designs explored was a two-beam structure as opposed to various other types of structures. Offering an overview, the I-beam is a very suitable structure for bending parallel to the web of the structure. However, it does not offer a solid response to two-directional, multi-directional bending to the web, nor does it perform well under torsional loading. However, they are widely used in buildings to support axial loads in columns of tall structures. Comparatively, the T-beam could be considered as the lesser cousin of the I-beam, since it's just like the I-beam, except it doesn't include a second flange. This absence of the second flange would reduce the overall tensile forces that the building would be able to withstand. Finally, the rectangular tube beam was the final idea assessed. Otherwise considered to be a hollow structural section, this beam offers many significant advantages. These include the ability to be highly resistant to torsional loads as compared to the I-beam. The structural beam also has the ability to resist significant deformation under multi-axial loading due to the similar rectangular geometry across two or more faces of the structure. Comparing the results of the validation process to the simulation model, the hypothesis could now be challenged. Assessing discrepancies between the deformation and the displacement, modeling our structure with the I-beam's position as the structural design of the building may have deviated the ANSYS results from the analytical results obtained from the second order ODE, which modeled instead a solid structure. Another point of discussion is that ANSYS calculated for the deformation of the structure, whereas the differential equation evaluated for the displacement. There's a relationship between strain deformation of a structure and the displacement of a structure. However, the values presented by both parameters cannot be considered to be the same. Considering that there is a proportional relationship between deformation and displacement due to the fixation of the building to the ground and a calculation of displacement at a specific height, the trend identified still holds true for the hypothesis created at the beginning. With regards to the beam structures, our hypothesis was satisfied with the rectangular tube beam incurring the least displacement. Regardless of the material, it could be seen that the stresses would accrue at the same points of the beam face. From this, it could be said that the rectangular tube beam dispersed the stresses across the beam at a more equivalent spread as compared to the other beams from the research and analysis considered. Therefore, from the suggestions of the paper identifying that the steel beams are better suited to study building displacements, and the fact that the sway of a building is more controlled when built with structural steel, since it has a greater stiffness and a higher damping constant, the hypothesis was supported fully.
So why does all this matter? Why take a simplified model of the stock exchange tower and model it using two ANSYS workbenches? Well, we're glad you asked, but somewhat disappointed that you may be asking this so late in the video. The implications of this study are very important for structural designers and urban designers alike, since adhering to building safety codes carry legal, monetary, and human life-related implications. Determining the material subject to the least deformation and the type of structural beam causing the least building displacement allows the civil engineer to decide what type of structure may withstand different loadings. Based on an analysis of the urban environment, the civil engineer can deduce which material would also bring the most return on investment. That is, which material can withstand the greatest or most average forces within an environment for the best cost. The simulation conducted in this experiment allows for a cost analysis to be performed as the next step, and perhaps an integration of a different I-beam, rectangular tube-beam, and T-beam structures within a building. Finally, this analysis allows for further research to be done in how to improve certain material properties for material scientists and engineers alike. Improving tensile strengths within concrete can surely be a focus of investigation for many material scientists, since this would offer a cheaper alternative to using structural steel within high-rise buildings or skyscrapers. With an analysis of how deformation propagates through a concrete structure, material engineers can develop further tests to improve tensile strengths of this brittle material, to perhaps reach a certain strain, as you could call it, of concrete, which would come close to tensile strength characteristics of structural steel or aluminum alloys. So what do you think? Do you feel swayed by our argument? Or did you have any interest in buildings in the first place? Yes, I understand you are mechatronics engineers, but when it comes down to it, ensuring that the human need for shelter is not simply met, but met with optimal safety, is an issue that concerns us all. This is only the start, though. More complex calculations could be made to define the stock exchange tower, and perhaps a more ideal and architecturally sophisticated solution could be proposed in the near future. In all, we are glad you joined us on this ride. Join us next week when we evaluate the structural integrity of E7 on Fun with Buildings. Goodbye for now.